Okay, I'll make a start. Yesterday we had left at this place where we said that a random process can be grouped in two classes, a homogeneous or stationary and a non-homogeneous process. Okay, so we had seen that a homogeneous or stationary process is where the probability description is unchanged for an arbitrary shift in the indexing parameter. And we had seen that the first order probability is independent of time or whatever be the indexing parameter. The second order probability would be not dependent on T1 and T2, but the difference of T1 and T2. So, the difference when we are dealing with the random processes, most of the times the full information is not available. What we have is the first few moments, the mean, the second moment, maybe the third moment, sometimes up to 5 moments. Beyond that, usually the value is not available. If it is available, it is fine. We would like to work with that. That is sort of the ideal situation when we have the probability description is given. If it is not, then we manage with the averages or the expectations. So, if you look at the second moment, which is the product of the two random variables or the random process at x at T1 and x at T2 multiplied by the joint probability description of the second order. So, there the time part would not be T1 and T2, but T2 minus T1, the delta T. So, when you integrate to get the second moment, either the central one, the covariance or the correlation, it is not dependent on T1 and T2 both, but only on delta T. So, that is for the homogeneous or the stationary process. For the non-homogeneous process, it is dependent on both T1 and T2. I hope it is understood. I will try to explain it further. What we have here, the second moment, the expectation of x at T1 into x at T2. I am not considering the central one. This is defined as double integral over, in general, this is for the general case, minus infinity to plus infinity for both the cases, and then it is x at T1 into small x at T2 into the probability density function joint x1 T1, this is x1 and this is x2. x2 T2 dx1 dx2 rather dx2. Okay. This is the general definition. This holds for the non-stationary process. But if the process is stationary, in that case this part becomes x1, 0 we need not write, x2 T2 minus T1. So, this is for the stationary process. So, when you integrate this, the second moment for the non-stationary process is a function of T1 and T2 both. For the stationary process, it is a function of this difference only. x1 and x2 are integrated out. When you substitute the limits for x1 and x2 and x2 do not come out of the integral. It is only the time part that comes out of the integral. And so, for the stationary process, this expectation is a function of the time difference. So, this difference is there between the stationary process and the non-stationary process. This makes the mathematics slightly simpler. So, most of the times when you make the first model for any random process in analysis, we start with this as a stationary process. And then while we examine, we find that it is not stationary, then we go over to the non-homogeneous or non-stationary process. So, as I said, the property introduces some simplification. Now, in all vibration problems, the frequency is very important. So, we talk of the spectral properties, which is the frequency properties of the process. For this, we define a spectral density function. For the non-homogeneous process, we call this as the generalized power spectral density function. This term has come from electrical engineering. They were the ones who first defined it. So, this power spectral density function, there is a proper theory how it is defined and why it is like this, but we do not have time to discuss it here. This phi xx subscript omega 1 omega 2 indicates that it is the density function of the random process x. There are two of these, so this is a bivariate definition. And this hat indicates the difference between the generalized power spectral density function that we call as the PSD function here, short form, or the simple PSD function. So, this is defined as a function of two frequency arguments, omega 1 and omega 2, as the double Fourier transform of the covariance function of x. This is the covariance function. Remember that this is a central moment. Okay. And then this has the argument, there is an I missing here, e to the power I omega 2 T2 minus omega 1 T1. This I is missing in the typing and integrated over time. So, once you integrate over time, these times should not come out of this integral, only omegas would come out, and this is the frequency breakup of the covariance function. So, it is like mapping the covariance function from the time domain to the frequency domain, and it is in a plane. T1 and T2 is a plane. So, one axis T1, other one T2. Here again it maps to a plane of omega 1 and omega 2. Of course, this definition is valid only when this integral is bounded. For many problems, this integral may not be bounded. So, you may have the covariance function, but you may not have the PSD function. So, this is the generalized power spectral density function, and the information is equivalent. If you know the covariance function, we can find the PSD expecting that it is bounded. If the PSD is known, by taking the inverse Fourier transform, we can find the covariance function. Now, for the stationary or the homogeneous process, this definition is simplified, as there is only one time, that T2 minus T1. So, we indicate this by tau. This is the lag period or the time difference between the two x's. This we call as the lag period. And you can see that this is the single Fourier transform, that I is existing here in the other expression that I was missing. So, this is 1 by 2 pi integral minus infinity to plus infinity covariance of the stationary process x e to the power I omega t dt. And by inversion, the covariance can be written in terms of the power spectral density function. This is the simple power spectral density function, no hat put here. So, many a times when we are solving a problem and for the excitation or the input, only the information up to the second moment is available, we find the response covariance either for stationary or non-stationary, and then to get the frequency breakup, we go to the power spectral density function, either the generalized one or the simple one. So, depending on how this power spectral density function behaves, we have some classifications. Probably you would have heard this name, the white noise process. Some of you have might heard it. This has the power spectral density function as constant. For this is a mathematically idealized random process. It is something like this. We are plotting this is for a stationary process. we are plotting over omega here from minus infinity to plus infinity. Actually, minus infinity negative frequency has no meaning physically. Frequency is always positive, but we still consider this as negative mathematically. And if the PhD function is flat like this is say phi naught, a constant value. This is known as a white noise. Mathematically, it is simple to handle. It is constant, not a function of omega, so integration differentiations are easy. There are other type of standard processes classified according to the power spectral density function. Like this is something very common. This constant white noise process is not a real process. Actually, this line that I had drawn, the area, it can be shown that the area below this, between the x axis and this line, indicates the energy content in the system. As I said that there is an argument why we have this definition of the PhD function. So, this indicates the energy content of the system, and a white noise starting from minus infinity to plus infinity will have infinite energy. So, theoretically it is easy to handle, but practically it is not a real process. There are many real processes like this. It would start at some omega naught and finish at some symmetrically. This is known as a bounded white noise. This is broken up. There are other types like this. I am drawing it here itself. It is a dotted line. Remember that this phi omega is symmetric in omega. With negative omega and positive omega, it has the same value. So, on this side also. This is known as a band limited white noise. This one is bounded. This is band limited. This is say omega 1 and omega 2. So, it exists only in this band. I will give you one example of a real power spectral density function. The unevenness of the track, the landing track, the air or the road has a form like this. It does not start from 0, somewhere here. It goes like this. This is a type of PhD function that we have for a road. Zero frequency, this frequency now is not the time frequency. When you are using the road, it is spatial frequency, radians per unit meter or per feet in terms of space, not in terms of time. Normally, frequency we say is radian per second, but spatial frequency would be in terms of the distance. So, it goes like this. Here, zero frequency means what? If you have a system with zero frequency means there is no oscillation, it is perfectly flat. In terms of the road or the track, it is perfectly flat. And what this indicates is, suppose we have the road here, this is the mean level and this is the road to some exaggerated sense. It may not have a flat mean, it may have a variable mean, it may have undulations like this in the mean. Over that you have the unevenness scattered. So, all those things are possible. So, basically zero frequency does not exist on the road. So, it is 0 here, and again to simplify the problem for analysis, we make it like this. We will let it extend and cut somewhere here, and this is the type of profile it has. We can say that as far as the analysis of the road, a vehicle running on the road and its vibration is concerned, we would consider that if the frequency is in this band, then it is important. If the vehicle frequency is beyond this band, then the road unevenness will not affect it. Okay, it will affect only in this range. Beyond this range, there is no interest, the oscillations would not be coming into picture. This was just some idea about how how we can characterize, understand the behavior of a random process looking at its PSD function. Now, after talking about the random variable, random process and its description, I wanted to show how we can use this for some solution, some problem solution. So, there are two approaches used here. This is about the modeling of the system. Basically, there are two components in the vibrating system, the structure and the environment with which it reacts. So, we model the structure depending on the need, the type of analysis that we want, we can model it. This is not only for random vibration problem, this is for all vibration problem. We model it either a discrete set of masses. So, you have the discrete or lumped mass systems, 1 mass, 2 masses, 3 masses, 4 masses, like that. We can continue to increase the masses, or we can model it as a continuous system. So, depending on what is our interest. If you are only interested in behavior of some point, how much deflection comes at that point, how much stress gets developed at some point, some critical point in the problem, then we can model this as a lumped mass. If you are interested in the complete global behavior, then we model it as a continuous system. So, we model the structure and we model the environment, both of these. The structure we model to have a mass, some stiffness to the linking of the different masses, or even for the continuous structure, and to have some damping property, dissipative property. So, stiffness and damping can be linear or nonlinear. The environment interaction gives us the excitation to the system. So, again, depending on the model that we have made, if there is single mass, there is excitation at that particular mass only. If there are more than one masses, then all of the masses may be excited, or some masses may be excited, some other may not be excited. In general, all these parameters that we are looking at, the mass, the stiffness, the damping and the excitation, they are random in nature. They cannot be defined completely with deterministic quantities. So, if you want a very accurate study, you define all of these as random, and we expect that the characteristics in the probabilistic sense is available to us, either the density function or in some cases the moments. Normal real structures are very complex, so we simplify the model to have a easy mathematical analysis. Usually, if you have the system also random, that is the mass, the stiffness, damping also random, then the system equation is a random equation. If you ignore the randomness in the system, which we cannot do in all cases, in some cases, like as a start, we would like to say that we consider the system to be not random initially. So, we will say that the mass, stiffness, damping is completely deterministic, given to us full information. So, the first study is started with the excitation as random. This is the simplest one to solve. So, here I have taken one example here of a single degree freedom system, mass, damping and stiffness. As I had mentioned earlier, normally when we consider something to be random, we use a capital letter, and if it is deterministic, we use a small letter. So, I have used this capital here for x to indicate that the response is random. The excitation is considered as random. In this particular example, M, C and K are not considered as random. To a long distance, the solution approach is same. We will see as we proceed further. It is only later on that the solution approach changes. So, in this example, we are considering F to be random. So, as F is random, the response is dependent on F. So, if F is random, X is also random. It has to be. Okay, that's why it is made as capital here. So now there are two solution approaches. I am describing here the first one. Here only ft is assumed to be random. The system equation can be expressed. This is another way of writing a single degree freedom system, can be done for higher ordered systems also. The whole equation is divided by m, the mass. So we can say that we have a system with unit mass, or whatever mass it has, in our measurement we take that as unit. Okay. So this is 2 xi omega n is c by m. Omega n square is k by m. This omega n square you know. This is the natural frequency of the undamped system. The same omega n comes here, and this xi is known as the damping coefficient, or sometimes the damping factor. Okay. So c by m can be shown to be 2 xi omega n. I am not doing it. I expected that Professor Wahi will do it. Anyway, so this is another form. Here this f1 is f divided by m. I have indicated here. Omega n is n square is k by m. This xi is c by cc, where cc is the critical damping, and f1 is f by m. The general solution can be put in two parts: the complementary function part and the particular integral part. Remember, yesterday when Pankaj was talking about this, he had put the form like this: a into some e to the power minus xi omega n t multiplied by a sin omega dt plus b cos omega dt. So this a and b we can break up. You remember that form. There were two constants involved. Here also there are two constants involved, a and phi. So that a and b can be expressed in terms of a and phi. So this is a more compact form, easier to handle. Also you can perceive what is happening here. Should I do the breakup? Okay, let me do the breakup. Where you had left yesterday was something like this. The complementary function x of c is e to the power minus xi. He didn't use xi, he had omega d here, xi omega n t multiplied by a sin omega d t plus b cos omega d t. Here I have used a there also, so I will use something else. What we do is, we write this a as say x cos phi and b as x sin phi. Can we do this? Yes, we can. A and b are constants, x and phi are constants. If we square and add, a square plus b square is x square. Okay. A by b, rather b by a is tan phi. So using those, we can relate a and b. Now if you substitute here, take x outside, what will we have? So this becomes now equal to capital X e to the power minus xi omega n t, omega dt into cos phi plus omega dt into sin phi. Can we write this as sin omega dt plus phi? So this is what I have indicated here. This is the phase angle. This x, which is written as a there, this is the amplitude, and this indicates the envelope. This is how the system is decaying. Okay. This is the way the system decays. Okay, so this is the complementary function part, and then I have left this particular integral as xp. The reason is there are two approaches to xp. We are considering, especially for random vibration problems, the excitation is not going to be periodic, or it's not going to be a harmonic function. It is a general function. So, assuming that f t is general or f 1 t is general, we are using the impulse response function here. This in the time domain, this h is known as the impulse response function defined here. H tau is e to the power minus I omega n tau divided by m omega d sin omega d tau. And this integral can be shown to give the particular integral. Particular integral is any solution. Remember that for the linear single degree freedom system or linear second order constant coefficient differential equation, all you need is a solution, because the solution is unique. Whatever you get has to be the solution. So, this is something that we get. The variation due to the initial conditions are taken care of by these constants here, this constant A and this constant phi. This will take care of the initial conditions. So, this is what we call as the time domain approach. There is a time domain approach. There is a second approach which we call as the frequency domain approach. There this capital H omega is known as the frequency response function. And for any general type of input, this is the form that it has, and this integral gives the particular integral. This can again be shown that this will satisfy the system differential equation. So, depending on which one we are going to use, that x p that I had left there can be put there. Now, we can find the solution or statistics of the response either in the time domain or in the frequency domain. And these constants that A and phi that are there, these depend on the initial conditions. So, depending on whether the initial conditions are random or not, they would be random or deterministic. There can be many situations where the initial conditions are random. One simple example is landing of an aircraft. When the aircraft lands, it comes down with a velocity that we call as the sink velocity. It also has a forward velocity because it is flying. So, it has a sink velocity and a forward velocity. So, that gives the initial condition. It has, as it is about to touch down, it has a landing gear that is extended. So, when it touches down, that collapses. So, at the time of touchdown, the system will have some displacement from the mean position. Remember that when you write this equation, the x is measured from the mean position. So, the aircraft touchdown is a situation where the initial conditions are random. Every time the pilot cannot come down with the same exact velocity. So, there will be some variation in the sink velocity, some variation in the forward velocity, that is known as the glide velocity. Okay, the extension would be same, that will not change because that depends on the structure of the landing gear. So, in that case, this A and phi will be random. So, that is a more complex situation. For this example problem, we are assuming that x and phi are deterministic. So, we are not taking the most difficult case, the simplest case we are trying. So, in the time domain, this is the solution, the complementary function part and the particular integral. Now, we are assuming here that for this excitation, we have the knowledge of the first two moments, the mean and the correlation or the covariance is given to us. So, we expect that the probability density function is not given. If it is given, then using this expression, we can find the probability density function of x. It is possible. It is complex, but can be done. If it is not given, then we have to make do with the moments. So, we take the moment of this x of t. So, we find the mean of x. So, that is the expectation of x of t. Remember that this expectation is an operator, and when you take it over the deterministic quantity, it remains as it is. The probability density of a deterministic quantity is 1. Okay, it does not change. So, this part we are assuming as deterministic, it will stay as it is. If we had considered the initial conditions as random, then we need some information about A and phi, and then we would write an expression like this here. Okay. So, this remains as it is. Now, the second part here, this expectation is taken before the integral sign. Now, knowing that the expectation and integration are both linear operators, we interchange the order. So, we take this integral outside and take the expectation inside. Here, this part is deterministic as it contains the system parameters. This one is random. So, only the mean of this is taken, which is written as mu of f tau. Okay. Mu of f tau S t minus tau d tau. By the way, this is also known as the convolution integral. Some of you would be knowing this. If you interchange the argument, then also it gives the same value. So, here we have h with the argument t minus tau, f with the argument tau. It can be f with argument t minus tau and h with tau. So, whichever is easier to integrate, easier mathematically to handle, we use that. Okay. So, this gives us the expression for the mean. So, what did we do? We have the expression for the solution, which is not exactly known, as f of t is not exactly known. But now we have one information about it. This one is now exactly known. This information would be given to us as some expression. So, we can integrate this and we get the value of the mean. Now, the second moment here, second moment, this is the second central moment, the covariance. This is the expectation of x t 1 minus mu x t 1 multiplied by x t 2 minus mu x t 2. So, I have written this in detail. Expectation of, we are writing this expression. Now, f t 1 tau 1 minus mu f tau 1, because we are integrating over the time domain. So, rather than writing this t 1 and t 2, because these would be here in the limits 0 to t 2, 0 to t 1, we have changed the variable inside the integral to tau, tau 1 and tau 2. Okay. Now, remember this expression of x. This is the expression for x, this is the expression for mu of x. So, if I take x minus mu x, what happens to these terms? These are both same. So, they cancel out. So, what you will get is here also inside the integration s t minus tau, s t minus tau. So, you will get f tau minus mu f tau. Okay. So, this is what is coming here. So, you have f tau 1 minus mu f tau 1 multiplied by f tau 2 minus mu f tau 2 into the h corresponding to the two times s t 1 minus tau 1, s t 2 minus tau 2 integral over tau 1 and tau 2. And then again we take the expectation inside the integral sign. So, we take the expectation of this term, which is same as the covariance of the excitation k f f tau 1 tau 2 s t 1 minus tau 1 s t 1 minus tau 2. Again, when this expression is known, we can do the integration. If it is difficult, then we do it numerically. Otherwise, we do it in the closed form. So, this is the time domain approach. We do exactly the same thing in the frequency domain approach. Only difference is that this part of the integral is in the frequency. Here it is not integrated over time, but integrated over frequency. So, exactly the same thing. This one has to be replaced. By the way, this f1 bar indicates the Fourier transform of f1. So, first that has to be obtained. Normally what would be given is the mean of f1 or the covariance of f1. So, from the mean and covariance of f1, we have to find the mean and the covariance of f1 bar. Okay. So, this is the expression for the frequency domain in the mean, and this is the one in the second moment, the covariance. Exactly stepped out the way we had done earlier, writing this term, then taking the expectation inside. So, this becomes the covariance of F1 bar at omega 1 and omega 2. Okay. So, this is the first approach. The second approach is I could not make the proper transparency for that. I will just explain from here. You see here, in the first approach, what we did was, we solved this differential equation, found the expression for the solution of x, and then by taking the different expectations, we found the mean and the covariance of x. Now, it is possible that we take the expectation here itself. If you take the expectation here itself, so I take the expectation of this whole equation. So, what will we have? We will have m into the expectation of x double dot, which is the mean of x double dot, c into expectation of x dot, which is the mean of x dot, and then expectation of k, which is the mean of x, sorry, not k, expectation of x, which is the mean of x. So, this differential equation, which is in terms of x, x dot, x double dot, comes out as mean of x, first derivative of x, mean of x, second derivative of mean of x. Can you see that? Let me write this. We have the equation like this: m x double dot plus c, this is small c, x dot plus k into x equal to f of t. This is small c. We are assuming that these are deterministic. So, what I do is, I take the expectation of the whole thing, the expectation here. So, term by term we consider here. So, this m is deterministic. So, first term becomes m into expectation of, and I am writing this as the second derivative of x with respect to t plus c expectation of x, okay, plus k expectation of x. Sorry. Okay, so, and this part here. Now, what about this? Can I write this as mu f of t, the mean of f, and this side here, this becomes plus k mu of x. Differentiation is a linear operator, expectation is a linear operator, you can interchange the order. So, when you take it inside, it becomes mu of x, and derivative of that is c plus, c multiplied by mu of x dot, or depends how you want to write this, mu dot of x plus m, same process again, mu x double dot. Okay. So, now instead of this differential equation, we have the differential equation in the mean of x, and this side you have mu of f. So, this is the second approach. Rather than first finding the response, then taking its expectations, you directly solve the differential equation in the moments itself. So, just like we took the first moment, you can take the second moment and even higher ordered moments, we solve the differential equation. Solving becomes slightly difficult. The reason is let me see if I can show that. I had used this example or this approach for a particular example of an aircraft in the takeoff run, and it was a multi-degree freedom system, non-linear system. So, this is the differential equation. This is the system equation. It's a multi-degree freedom system. So, this M is a matrix, C is a matrix, the mass matrix, the damping matrix, and the stiffness matrix. Z is the response vector, it is a vector. So, Z double dot. G1 a function of Z dot and T is the non-linear part of the participation in the damping, and the damping matrix is kept as linear, but there is a function put here, a nonlinear function that gives the participation of damping. Similarly, G2 is the participation of the stiffness. Okay. So, for this I had used this approach. I will try to show you the equation in the modified form. These are the two equations for the mean. After the expectation is taken, mu z, and this is the expectation of the nonlinear function. This is a z dot here, the expectation of the other nonlinear function due to the stiffness, and the expectation of f of t. This is for the first moment. If we know how this function is, the expression, then we can find this expectation. Similarly here, this is the second moment. In this case, not the covariance, the correlation has been taken. That is, mean has not been subtracted. So, this time you get this equation for the second moment, and then with the properly known initial conditions, these equations can be solved. This being a nonlinear equation, you have to do it numerically. Suppose it was a linear equation where this was just z dot and this was just z. In that case, we could have done it by hand also. We could have obtained the closed form solution. So, just wanted to show that this is the expression that you get for the second moment, and I will try to go to the solution. The data is taken for a light passenger aircraft. This is the model. A very simple model is made. This is for the aircraft landing gear. This corresponds to the tire. The tire is given a stiffness. Tire has only air, so the damping in the tire is neglected. This M2 is the landing gear mass, the total landing gear mass, and M1 is the share of the mass that comes to that landing gear. Usually, there are more than one landing gear for an aircraft. So, there are 3 in the tricycle type. So, depending on which one we are analyzing, this will not be the total mass, this will be the share of the mass for that landing gear, and the stiffness and damping. This is a linearized problem here. Z1 is the response of the upper mass, we call that as the sprung mass. Z2 for the second mass, that is known as the unsprung mass. Then the runway has a mean unevenness, which is not constant, it is not flat. Then a random superimposed value like this is indicated as h of s. Now, I have the solutions here. There is a slightly modified mean response. This is for the takeoff run, remember. So, this axis is very expanded. So, when the motion starts, by the way, from the response of the first and the second mass, this mean value of the runway is subtracted, because that also comes in this value. So, actually this will give the oscillations of the masses, and this is the mean value. When it starts with a shock. So, it has a large displacement, and gradually as it runs, this drops out. The reason is, as the aircraft runs, the lift increases. As the lift increases, the effective mass reduces, and finally at the takeoff time it becomes 0. So, that is why this is reducing. This is the second moment, the correlation function. Every time the zoom is changed, it goes to the top. Okay, let me explain with this itself. Here, this is the sigma squared value for Z1, that is the upper mass. These different curves are for different type of acceleration during takeoff. All the time the same acceleration may not be there. So, these firm lines are for a larger acceleration, the dotted ones are for a smaller acceleration, and this runway had a sinusoidal unevenness. So, these peaks are corresponding to those inputs of the peaks of the sine wave, and as you can see, as the speed increases up to takeoff, the distance between these peaks increase, because in that time, in that period, this is against time. So, in that period the distance covered is more. Okay. So, that is how it goes up to the takeoff. The value is not given beyond the takeoff. Just after takeoff, with some oscillations, it would have died down. There is a very similar graph for the first mass, that second mass also. Not much different. I think I will stop here in this part, and I would like to discuss the syllabus for this type of. This is a second level course, not a first level course. So, it is expected that whoever is taking this course already has some background in vibration. The type of things that we cover here is gone. The type of things we cover here is introduction to probability theory, random variables, description of random variables, that is the different probability function, expectations, the characteristic function, etc. Then the functions of random variables. So, if the description of the independent random variable is given, how we can generate the characteristics of the dependent random variable. Then we go to the random processes and its description. We talked of all these things in very brief and short manner. Properties of random processes, this is something that we use when we go for design. There are different properties of random processes, like suppose we are looking at the displacement as a random process, then depending on the device that we are examining, this random process will have a nature of first time crossing a level. Suppose it is displacement or stress. So, properties are like level crossing. So, if it crosses a particular permissible level, up to a permissible level, it is fine. If it crosses a level where the structure breaks, that type of analysis we can do. What is the first time it will cross, how many times it will cross, how much time it will dwell beyond that level. So, all these properties we discuss here. Then the response of a single degree, multi-degree and continuous systems to random excitation. I tried to show something today. Failure due to random vibration, this is again the design application, because there can be different types of failure. There can be catastrophic failure when the stress goes beyond an allowable limit. That can be a fatigue type of failure when the stress is still low, but there are a number of cycles coming again and again, like what happens in the landing gear of an aircraft. It is designed to take that type of load, but it is having a repeated loading. And every time it takes off and lands, that loading is repeated. So, there it can have a fatigue type of failure. Then application to aero, civil and mechanical systems. So, this is a short description of what we teach in this course. There are some books that are very useful, which I have used as a textbook for the course. These two, Introduction to Random Vibrations by N.C. Nigam, is slightly old, but it is still the best book in the market. Probabilistic Theory of Structural Dynamics, it is still older, but gives a lot of information. Then there are some more recent books, 2006, 2005, 2004, and this is an old one. This book of Random Vibration in Mechanical Systems by Crandall and Mark. S.H. Crandall is the one who wrote that Mechanics of Solids book. This is a book that I think one should start with. This for mechanical engineers, it is written for mechanical engineers, and it gives you an understanding where you can use the random analysis and why you should use the random analysis. This is a small book, very thin book. Okay. So, there are actually two types of books in random vibration. One is those that I have listed here for engineering applications. So, their theories of as far as the probabilistic theory is concerned, it does just touches on those things that are needed for the description. It does not go into the details of the probability theory, but goes more to application to engineering problems. There are some other type of books written by mathematicians, where they delve more into the probability theory, theorems, lemmas, their proofs, etc., and just touch on the application to mechanical or other type of systems. So, otherwise there are almost hundreds of books in this area. So, you can pick up any of these, try to read this. This one can read by yourself. You do not need anybody's help. Here for the others you need some help. I think I will stop here, and any questions you have. We expect that this should be a graduate level course or a course at graduate level open as elective to undergraduates. Okay, I think I will stop and